Hi guys, how's everyone doing? Today I would like to talk you about as a topic high pass filter. This presentation is divided into 8 parts. Part 1 Group Member, Part 2 Introduction, Part 3 Procedure, Part 4 Simulation in Multisim, Part 5 Results, Part 6 Waveform, Part 7 Discussion, and the last part is Conclusion. So, I want to begin with my group members. The first member is Muhammad AKMAL bin MUSTAFA KAMAL. The matrix number is B082110019. Secondly, AMIR NAZRIN bin AMIR HUSIN. The matrix number is B02110317. And the third member is me. My name is Siang Cheng. My matrix number is B082110238. And the last member is ELSON WONG. The matrix number is B082110108. Next, we are talking about introduction. A high-pass filter is a filter that allows only signals with frequencies which is higher than the cut-off frequency to pass through while attenuating the signals with lower frequencies. The cut-off frequency is determined by the filter's design. The output is drawn across the resistor while the input signal is applied to the capacitor. All the signals below the cut-off frequency level are attenuated by the filter. The gain of a high-pass filter increases as the frequency is increased. The cut-off frequency FC is determined by the circuit's R and C values. The cut-off frequency is inversely proportional to the time constant when the time constant is equal to RC. This is the example for the high-pass filter circuit. To calculate the cut-off frequency, which is FC, we're using the formula FC equals to 1/2 pi RC. Besides that, to calculate the phase shift data, it is equal to arctangent 1/2 pi FRC. Next, to calculate the voltage gain AV, it is equal to V out over V in, or equals to R over Z R square plus XC square. XC is equal to capacitive reactance. Besides that, AV is also equal to R over Z. At low frequency, the capacitive reactance is equal to infinity and the V out is equal to 0. However, at high frequency, the capacitive reactance equals to 0, the V out equals to V in. Next, let's move on to procedure. Step 1. Put together the circuit in figure 1. This figure 1 will be shown in the next part, which is simulation in multisim. Connect the oscilloscope's channel 1 to the input voltage Vin and adjust Vin to a frequency of 100 Hz with an amplitude of 2.0 Vp or equals to 4.0 Vpp. This Vpp means that the voltage peak to peak on the oscilloscope display. Step 2. Connect the channel 2 of the oscilloscope to the resistor R and measure the output voltage Vout amplitude Vp. The table 1 should be filled out with the results. Increase the function generator's frequency to the frequencies listed in the table. Next, adjust the function generator's amplitude so that Bein remains at 2.0 bp or 4.0 bpp on the oscilloscope display. For each frequency, calculate the amplitude Bp or Vout. The last step is adjust the frequency of the function generator until the Vout is equals to 0.707, and this value is a Vout max to get the cut-off frequency Fc. Make a note of the measured cut-off frequency in the box below. In part 4 is the simulation in multi-C. This is the RC high-pass filter circuit. The frequency of 100 Hz with an amplitude of 2.0 Vp was set in function generator. For the channel 1 of the oscilloscope is connected to the input voltage of the circuit, and for channel 2 is connected to the resistor. In this circuit, the value of capacitor we use is 470 nanofarad, and for resistor is 330 ohm.
For the part 5 is result. As you can see, this is the result from 100 Hz until 10 kHz. For the 100 Hz, the Vout is 193 MV, and for the AV equals to Vout, Vin is 0.0965, and AV/dB is negative 20.31. Next is 200 Hz. For the Vout is 382 MV, and for the AV equals to Vout Vin is 0.191. For the AV/dB is negative 14.38. Next is 400 Hz. The Vout is 726 MV. For the AV Vout Vin is 0.363, and the AV/dB is negative 8.8. After that is 800 Hz. For the Vout is 1.23, and the AV Vout Vin is 0.615. After that, the AV/dB is negative 4.22. For the 1 kHz is 1.4 for the Vout. For the AV equals to Vout Vin is 0.7, and AV/dB is negative 3.1. For the 2 kHz, Vout is 1.78. For the AV equals to Vout Vin is 0.89, and AV/dB is negative 1.01. After that, 4 kHz, the Vout is 1.94. The AV Vout Vin is 0.97, and AV/dB is negative 0.26. For the 8 kHz, the Vout is 1.98, and the AV Vout Vin is 0.99, and for the AV/dB is negative 0.087. Lastly, 10 kHz, the Vout is 1.99, and for the AV Vout Vin is 0.995, and AV/dB is negative 0.04. So this is the data plot. You can see from the 100 Hz until 10 kHz is increasing. Next, part 6, waveform. This is for 100 Hz and 200 Hz waveform. To that, 400 Hz and 800 Hz. After that, 1 kHz and 2 kHz. Then 4 kHz and 8 kHz. And lastly is 10 kHz. Part 7, discussion. The first order high pass filter requires a capacitor with a very high capacity, which causes very high fundamental losses, and therefore it is rarely used. The first derivation process is as follows: CV equals Q. C represents capacitance, and for the V is for the voltage, and Q electric quantity. You can see from this diagram, for the loop current is dq over dt equals to dCbC over dt equals C dVC over dt equals to YT over R, or VC T equals to XT minus YT, where the C dVC over dt equals to C dVXT minus YT over dt equals to YT over R. For the Laplace transform, RC SXS minus SYS equals to YS. YS over XS equals to 1 over 1 plus 1 over RCS, or GS equals to 1 over 1 plus 1 over RCS. The differential form is RC dyT over dt plus YT. It's equals to RC dXT over dt. Next, the second order high pass filter has the best performance but causes higher fundamental losses compared with the other type. The second order filter means that the filter contains the second order differential in the time domain expressions, or the highest order of S of the transfer function. Denominator is 2, and the gain of the filter to DC component is 1. We can see from the diagram A and B, it is a second order high pass filter circuit voltage control. For the A is HPF, and for the B is HPF frequency characteristic. From the diagram beside, pass band gain. This is for the formula. ABP equals to 1 plus RF over R1. The transfer function is AVS equals to SCR square AVP over 1 plus 3 minus AVP SCR plus SCR square. So for the frequency response is where F0 F equals to 1 over 2 pi CR, or Q equals to 1 over 3 minus AVP. The expressing formula can be found AV equals to AVP over 1 minus F0 over F plus J1 over Q F over F0. The conclusion for this, when F is less than F0, the slope of the amplitude frequency characteristic curve is plus 40 dB. When AVP is greater than or equal to 3, the circuit self-excited. This is the multi-channel feedback high-pass filter. Voltage transfer function of this circuit, Hs equals to K S square R1 R2 C2 C3 over 1 plus SR1 C1 plus C2 plus C3 plus S square R1 R2 C2 C3. Relationship between circuit parameters and components. For the omega C equals to 1 over power source R1, R2, C2, C3. Q equals to power source R1, R2, C2, C3 over R1, C1 plus C2 plus C3. Or K equals to negative C1 over C2. This circuit is designed with equal capacitance. That is, let C2 equals to C3 equals to C, and C1 equals to KC. That is, omega C equals to 1 over C power source R1, R2, or Q equals to 1 over K plus 2 power source R2 over R1. Next, conclusion. The conclusion of this lab is that we now understand the theory of filtered characteristic. That is, high pass filter allow frequency above the cut off to pass. This lab makes students in deep understanding about the advantage of this function in industry. These functions are great when we used correctly. For example, is to clean up any unwanted signal, tidy up the signal arrangement, and many more. Thank you.